Hello, everyone. Bonjour, tout le monde. Um, so I'm Claire. I'm standing in for Luc Vinet today because he's traveling. Um, I'm an assistant professor in computer science in Tirol and at Ivador Mila and Courtois Institute. So it's a real pleasure today to introduce Lucien Hardy from the Perimeter Institute. Um, Lucien was actually one of my mentors when I was a postdoc at the Perimeter myself, so I'm very happy to have him here. Um, Lucien did his studies at Imperial College London, where I also did my studies, so very nice, and then a PhD at Durham. And in 1992, he discovered what is known as the Hardy paradox, which is a really interesting thought experiment, which shows that you can have particles and antiparticles kind of seemingly traveling through each other without annihilating. And this also led to Hardy's theorem, nicely named, which is a sort of proof of non-locality or Bell non-locality in quantum mechanics, and a very particularly simple one. Lucien has, since his studies in the UK, he's worked in all sorts of places around the world, including in Rome and in Oxford. And he has been a faculty member of the Perimeter Institute for Theoretical Physics here in Canada, in Waterloo, Ontario, almost since its founding many, many years ago. So yeah, without further ado, please welcome Lucien to talk about operationalism, causality, and quantum theory.
Is it working now? Good. So I won't pass upon the opportunity to congratulate Gilles Brazard here for winning the Turing Award. This is commonly regarded as the Nobel Prize of Computer Science, and he and Charlie Bennett, the announcement was made a few days ago, very, very worthy winners of that award. So congratulations to you. Okay, so my background is in foundations of quantum theory, which is a field that's been historically very closely connected with quantum information and quantum computing. Really, quantum information is about turning the mysteries of quantum theory, making them useful, making them do some work for us, and what I'm going to talk to you about today is about time symmetry in the quantum framework. Um, so this is the title. Let me just go through the words in the title. Operationalism is just the attitude that that you have when you do an experiment. You have boxes, and they have settings on them and outcomes, and so you take the attitude that these boxes, they have inputs and outputs, and you're thinking about the world in operational terms when you regard it with respect to the settings and so on. It's an attitude that's very natural to people from a computer science background, because you have gates and circuits in that context. Causality is a very basic principle in physics, and we'll see in the context of time symmetry, causality becomes even more interesting. And what I'm going to do is, I'm going to apply these ideas of operationalism and time symmetry at a very general level, and then I will apply it specifically to quantum theory, and from this time symmetric perspective. And let me just show you some pictures. So I recently put on the archive a 700-page book which I'm sure everybody has read. But if you haven't read the book, here is a quick summary. Okay. Oh, that's okay. Well, the pointer is not working, but let me just look at the top row. So the book has two parts. It has the simple book and the complex book. By complex, I mean complicated. The first half is where you consider operations, and I will talk more about what an operation is. But on the left-hand side there is a box which is an operation. It has some inputs and some outputs. So input A, output B. And then we apply it to quantum theory. In quantum theory, we have operations. So the next box has an operation, B hat, has the same input and output. And then we're interested in objects that live in Hilbert space. So Hilbert space is space that's important for quantum theory. And so over here we have on the left a left Hilbert object, and on the right a right Hilbert object. The complex book has the same objects in it, but now the inputs and the outputs can have a more complicated relationship with one another. So in the simple case, the inputs are before the outputs. All the inputs are before all the outputs. But in the complex case, some of the inputs may be after some of the outputs. So this is a more interesting situation that we can consider. And I think it's an idea that has application, across physics, computer science, many places you might think about this. Okay, and then the connection between these objects is that this first object, the operation, can be made to correspond to the second object, the operator, and that is equal to a certain object defined in terms of left and right Hilbert objects. Okay, so there's the sort of basic picture. Okay, so let's think about time symmetry. The great fundamental theories of physics. You have a question? I'm delighted to take questions. Yeah, yeah. Okay, so the first, I will talk about this, but the first one is it points to an object in the laboratory.
In what, sorry?
The first one points to an object in the laboratory.
In the
Laboratory.
poetry?
Laboratory, the place where physicists
A
do
laboratory.
experiments.
Sorry.
Yeah.
Sorry.
Yeah, in the laboratory. Yeah.
Yeah.
Like like it could be a laser or a lens or a detector, something like that. And the second one points to an object in your notebook. It's a mathematical object.
Okay.
So you want to have a correspondence between the stuff that happens in your experiment and the stuff that happens in your calculation.
And how about the third one?
And what, sorry?
The third one, please. The third one. The
third one is well, the third one is, I mean, I won't get much into the third part of the thing, but it's a way of writing down these operators that you need to do calculations in terms of more basic objects. Okay, so there's this nice diagrammatic language that you can use.
Thank you very much.
So for those who know it, there's a thing called doubling up.
Yes.
Yes. Okay.
I know it.
Yes. Good.
Thank you.
And what I've represented there, in fact, is the Krauss decomposition.
Yeah.
Yeah.
Oh, thanks.
Yeah. Okay. Good. Good questions. Okay. So all the great fundamental theories are time-symmetric. Newton's laws of mechanics, Maxwell's equations. Interestingly, Maxwell's equations, the form that we read in the textbooks, were actually written down by Oliver Heaviside, Oliver simplified tremendously, reduced the number of variables, and wrote the equations down in a form which is familiar to us today. It was really the equations of Oliver Heaviside that Einstein was staring at when he was thinking about special relativity. And then we have Einstein's theory of general relativity, the Schrodinger equation. All of these are time-symmetric. And in the case of the first three theories, they're classical, and they're not really problematic. But in the case of Schrodinger's equation, or in the case of quantum theory, the time symmetry is a little bit more problematic because you have measurement. When you make a measurement, you collapse or you project the wave function. And this looks like a time asymmetric process. Well, the story is a bit more complicated than that. There's a formalism due to Aharonov, Bergman, and Leibowitz, where they show that you can make quantum theory time symmetric by thinking about pre and post selection. But then the story is more complicated than that, because their formalism only works in a restricted set of cases for what are called pure quantum states. When you go to the general quantum theory, that doesn't work. And so the work I'm presenting is a way to make quantum theory time symmetric yet again in this general operational theory. Okay. So let me talk a bit about the time asymmetry we see in standard quantum theory. Actually, to make it even simpler, let's talk about the time asymmetry we see for classical bits, so a 0 or a 1. So you can imagine an experiment where you have a box A that prepares a 0 or a 1 with some probability in the 0 and some probability in the 1. This is a very simple thing. And so then, well, you want the probability that it's in 0 plus the probability that it's in 1 to add up to 1. So the state that you prepared should lie on that line in the graph there. Oh, there, I've managed to find the pointer. Okay. Now, actually, it turns out to be practical to allow the P0 plus P1 to be also less than 1, as long as it's greater than 0. That's useful for various reasons I won't go into. And so actually, this whole all the space underneath the straight line is also allowed. So the state can correspond to any point inside this triangle. Okay. Now, the experiment you could do at the other end with the box B, it might be, you might just decide to see whether it's a 0 or a 1, or you might decide inside box B to do something more probabilistic. You could have 2 coins inside that box, and you toss, 2 different coins, they're differently weighted. You toss, the one coin is labeled 0, the other coin is labeled 1, and you toss the coins, and you use those coin tosses to decide whether to output a yes at the end, or to say this thing has happened. So then the probability you get would look like this. It'll be the weighting of those coin tosses with the probability of it being in the 0 or the 1 state. Okay, so that's a very general thing you can do. And now we have this thing called an effect, which is associated with the B box, and the space of allowed effects looks like this. It's a square. This looks very time asymmetric. Actually, what I want you to do is, instead of thinking of this as a triangle and this as a square, I want you to think of this as a cone. It's a 2-dimensional cone with a flat top, if you look at it on its side. And this is a double cone, also in 2 dimensions. Okay, so this looks very time asymmetric. But this is also what we do in quantum theory. So in quantum theory, we have qubits. This is the analog of bits. And a qubit, the states live, well, I can't draw, it's a higher dimensional object than I've drawn here. The states live in a 4-dimensional cone, which has a flat top. The top of the cone is the block ball, for those of you familiar with that. And then we taper down to the origin to consider states which are subnormalized. And then the effects, they live in a double cone. So you have this kind of shape. Then you can also look at general operational theories. So not just classical bits or quantum bits, but you can consider all sorts of general operational theories. And in those also, in the sort of standard way of doing this, you have the states are cones, the effects are double cones. So this, all of this looks very time asymmetric. Yes, go ahead, Claire. In which one? Sorry, in the quantum?
If you go to the classical one. So
yep.
Why is it a square here? Like the W1, W0 don't add up to 1.
Yeah, okay. So the most general, so one thing you can do, which corresponds to the point in the top corner here, is just always output yes. Okay, so whether you have heads or tails, you always output yes. Okay, so that point, so you want, and that corresponds to where you just add together P0 and P1. And if it's normalized, if the state is normalized, you always output yes. So you definitely want that point. Okay, the more general thing you can do is have 2 coins inside that box B. You toss 1 coin. If it comes up heads, you look and see if you have a 0. If you have a 0, you output yes. You look at the other coin, you toss that coin. If that one comes up heads, you look and see if you have a 1. If you have a 1, you output yes. So that's the kind of space that you're expecting. These 2 weights, each coin has its own weight, and these weights vary between 0 and 1. Is that kind of clear? Yeah. So this is where you get the double cone structure.
Thanks.
Yeah. If you turn it on its side, it's a 2-dimensional double cone. Okay. Okay. So this is the usual picture, and it's time asymmetric. What I want to do is to go to a time-symmetric picture, and what happens in the time-symmetric picture is you get something like this. You have a double cone in each case. The states live in a double cone, the effects live in a double cone. And clearly, if you have a time-symmetric picture, then you want that to be the case. Otherwise, it's not time-symmetric. These states and effects, so these spaces I've drawn here come from a deeper theory, which I'm going to show you. I don't just draw them because I like them. They come from some deeper theory. And to make the theory time-symmetric, we have to sort of revisit the basic notion of what an operation is in these kinds of theories. It turns out that one of the reasons it's time, I've seen your hand, one of the reasons it's time asymmetric is because people have been making the basic notion of an operation time asymmetric. Yeah, go ahead.
Yes, so I'm used to thinking when quantum information about qubits that are either the state is a linear combination of vectors 0 and 1.
Yeah.
So, and this is a new way to represent states for me with geometrical shape. What would a qubit look like in this cone?
Okay, so are you familiar with the block ball? So that's
the block bowl or sphere?
Or sphere, yeah, block sphere, sure. So the block sphere is on the surface of the block ball is the block sphere, and those are the pure states. And on the interior, inside the ball are the mixed states. Okay, all of those states are normalized, so the diagonal entries add up, of the density matrix add up to 1. But you can consider taking subnormalized states where the diagonal entries add up to something which is maybe less than 1. And that gives you this cone that goes down to the origin. So the block ball is on top, and you go down to the origin. Yeah, and that's the usual picture. Maybe I should explain, because I went past this too fast, but the reason I want to consider the subnormalized states is because it's possible, this box B, I said, it can output a yes. That could be like a light that flashes, okay. And then you say you got the result you were looking for. Well, box A could also output a yes. We'll have it. This could be the outcome, or no. So there could be a light on box A that also flashes. And but that light might not necessarily flash. So then you can consider states which are subnormalized. Okay, the normalization is equal to the probability that the light on box A flashes. So it's very useful to consider subnormalized states in this kind of framework. Okay. Okay. So let's oh yeah. So there's two things I wanted to mention just at the beginning. One is the equivalence of this framework, the time-symmetric framework, with standard quantum theory. And the other is linearity. So let's talk about equivalence first. The standard operational quantum theory you read in the textbook, which has density matrices, completely positive maps, POVMs, all that stuff, for those of you familiar. That I'm calling that the time forward framework. It's the standard point of view. The time symmetric framework I'm going to show you is equivalent to the time forward framework. And that's a bit strange at first, because if I go back, I have in the standard framework, I have this space of states, whereas in the framework I'm going to show you, the time symmetric one, the space of states is like this. It seems like these are different theories. That's not the case. They're the same theory, but you're packaging the probabilities in a different way. And in particular, in the standard approach, there are certain probabilities that are conditional probabilities. But in my time symmetric approach, I end up using joint probabilities instead. And so that's the reason that you can have these different shapes. Okay. And now on linearity, in the time symmetric approach, like I just said, we use joint probabilities, whereas in the time forward approach, we have these conditional probabilities. Now, it turns out that the usual approach to quantum theory is linear, even though we use conditional probabilities. When you can write a conditional probability down in terms of joint probabilities by dividing, everyone is familiar with this, the conditional probability of A given B is equal to the joint probability of A and B divided by the probability of B. Okay, so that's a nonlinear equation. In the usual time forward approach, we have this conditional probability conditioned on stuff in the past, but that denominator turns out to be trivial, and the reason it's trivial is because of the causality conditions we impose. Okay, so standard textbook quantum theory is linear, but it's only linear because of the causality condition we use in standard quantum theory. Whereas the time-symmetric approach is linear, even if you don't need, even without reference to those causality conditions. Okay, so the time-symmetric approach is more deeply linear, and I think that may be important when we go to a theory of quantum gravity, which is another interest of mine and many people at Perimeter, because linearity makes life so much easier. And so being in this time-symmetric setting should help. Okay. Oh yeah, I just said some of this stuff already. So I think that the time-symmetric perspective is going to be more fundamental. Part of the reason I believe that is because I just wrote a 700-page book and I want to promote it. But I also believe it because of the points about linearity I just made. Certainly, sometimes a change in perspective is very useful. So if you think about Einstein's elevator, he thought, well, let's think about somebody who's in an elevator and they're falling, so their frame of reference is fixed with respect to that elevator, and in that elevator, gravity disappears locally, and that insight was very important for his development of general relativity. So a change of perspective can be very useful. Yeah, and I think I made the other points before. I should just mention various, there's lots and lots of work that's been done on operational quantum theory and general probability theories and all this stuff, and I tried to cite a lot of it in the book. The main influences, well, some of this grew out of my own work, but the main influences I want to draw attention to are, there's the work of Robert Urkel, who has this thing called a general boundary formalism. He's a quantum gravity researcher originally, although he now interacts a lot with the quantum foundations community. And he was already thinking about what people call higher order quantum processes back in 2002. I think he was perhaps ahead of the game. This work adopts a lot of the diagrammatic thinking that goes back to Penrose, but then also many of the people, and Bob Kirker in Oxford has been the sort of chief advocate of that in recent years. Once you've been converted to diagrammatic calculus, it's sort of hard to go back, and at some point I was converted. This work has at its core, although I don't know I'll have time to really go into the details, ideas from quantum strategies. This was work by Gus Gutowski and John Watrous, in Waterloo. Interestingly, I wasn't really interacting with them so much as I was interacting with the other people who were initially in Pavia, so that Giulio Chirabella, Mauro Dariano, and Paolo Perinotti. Giulio came to Perimeter for a postdoc, around about the time this work was happening, and they were interested in these objects with complex causal structure, so where not all of the outputs are after all of the inputs. So these things are very interesting, and a lot of people are thinking about that in quantum information and quantum foundations. And then some ideas on time symmetry was influenced by, there's a paper by Andrea Di Biagio and other people from 2020, and certainly we were talking, and that influenced me very strongly. Okay, so let me give you a kind of outline of the structure of this work, and it relates to those pictures that I had on the title page. So we start with an operational descriptive framework. Okay, I'll talk about that on the next few slides. This is really describing what happens in the laboratory during an experiment. And then we introduce this thing, I call it a P function, basically a probability function, and we get this operational equivalence framework. And then we have correspondence, if we want to go to quantum theory, with these operators. We have a framework for those. And then there's also these Hilbert objects. I talk about the left and right Hilbert objects that feed into that. We'll see how much of this we get through. I'm going to mostly talk about the simple framework, so the simple causal structure objects, even though the complex stuff is much more interesting, but I simply won't have time to talk about that. Okay, so first of all, the operational descriptive framework. Okay, so it begins with what sounds like a joke. A theoretical physicist walks into a laboratory. I don't really have the punchline, but we all know that's a very bad thing. I think it is, yeah. Yeah. Now, of course, before he walks in or she walks into the laboratory, it's very important that they sign a document to promise not to actually touch anything. But you're allowed to look at the apparatuses. And so what do? Well, they draw a picture. Okay. Now, this is a picture of a schematic picture of the experiment. Of course, different experiments will have different schematic pictures. And of course, this is an idealization. It misses out all sorts of details in the laboratory. For example, there's lots of wires that connect, detectors to coincidence monitors. There's maybe a half-eaten piece of pizza in the corner. There's blinds that come down to stop stray light. There's all sorts of stuff in there, which is not relevant, but this is meant to capture the essential part of the experiment, and it consists of these things called operations. An operation is one use of a piece of apparatus. Okay, so an example might be a lens. You have a photon goes in and out of the lens or detector, or whatever, a laser or many other things in the laboratory. Okay, so this is the operational description. And operations are usually conceived of like this. So you have this box representing a piece of apparatus. You have inputs and outputs for your physical systems, for your quantum particles, perhaps. Okay. Then on the apparatus, you may have some knobs that you can set. These are the settings. The setting is information which is available before and after you've used the piece of apparatus. And then also you'll have some outcomes. Okay, this might be a light that flashes, a detector that clicks. So you have these outcomes here. And that's a sort of picture of operations that we normally have. But this picture is not time-symmetric, clearly. Something is missing. And to make it time-symmetric, we have to add one more wire, which is an income. Okay. And so here, by an income, I don't mean something which appears in your bank account once a month, or if you're lucky, but rather this is the opposite of an outcome. It's like some information that comes in rather than goes out. So the income is available before, but not necessarily after. Sorry, go ahead. Oh yeah, so the inputs are like your quantum systems, whereas the income is a classical thing. Yeah. I thought you were going to ask what the difference is between incomes and settings, but I think I've answered that. Yeah. Okay. In quantum theory, one way to provide an income is to have some classical information that chooses one of a set of orthogonal quantum states, and then you send that quantum state in, and then that quantum system gets eaten up by your operation, and so you lose that information. Okay. Okay. So instead of drawing that every time, I'm going to absorb the setting into the symbol that appears inside the box, the B. So if the setting is different, then you would write B prime, perhaps, instead of B. And so now, and then I put some, I use these symbols to denote the small a, small b, small c, to denote the systems that come in. And then the incomes and outcomes, I'm going to call those pointers, because in the quantum foundations literature, often we talk about the pointer reading where you read off the outcome. Okay. Okay. So I'm going to start to talk about this framework a bit. So one thing we have are ignorance boxes. So this is a box which you can place on a pointer or on a system. You just basically, either it feeds in noise or it just ignores that. These are, so I call them ignorance boxes. Often in the literature, these things are denoted by these kinds of earth symbols. These boxes correspond to, remember in the double cone, the double cone thing I drew, these boxes correspond to the top point of the double cone, the apex at the very top of the double cone. Okay. And so they're actually unique in the sense that they're the only normalized, or I call deterministic, boxes like this, and they live on the very top point of that double cone. Something else which is important is readout boxes. So let me just show you this picture. So we place a readout box on these incomes and outcomes. So like I've drawn here. So first of all, we send in this box R. We have a readout box, and then we could also have a readout box on the outcome. And this is where we get the information, whether it's X or Y, as to what the what that readout was. Okay. And just a bit of terminology. If an operation has some implicit readouts, like here I've defined that like this. So there are some implicit readouts. Then I represent it by non-bold font, and I call it indeterministic. And if there are no implicit readouts, then I call it deterministic. Okay, this is the terminology in the literature. Okay. And we can wire together these operations like this. And a circuit is when we have no open wires left over. And a network is if there are some open wires. Okay, and now, well, that's the operational descriptive framework. So now I want to come to the next bit, which is the operational equivalence framework. Okay. So far we have a description of stuff in the laboratory. And now this theoretical physicist has to do what theoretical physicists do best, arguably, theoretical physics. So this works like this. We start with an assumption about probability. Okay, and here is the assumption. And I claim this is a deep assumption. So we assume that the probability of a circuit depends only on the description of that circuit and not any extraneous details. Okay. So the probability, this is the probability that you see the readout W, Y, and X and Z, the readouts, given the specification of this circuit. Okay. Once you've got that assumption, you can do all sorts of magic. Go ahead. So I'd say the reason I need this assumption is so I can set up. So the reason I need this assumption is so I can set up the sort of the framework so that basically a linear framework for the general probabilistic framework, which I'll talk about a bit. But that, I'm not entirely sure I understand your question. One thing, okay, maybe I can explain why this is a deep. Well, you want to clarify more, or?
No, yeah.
Okay, so one thing this assumption does is it tells you that you've characterized your apparatuses appropriately. So let's imagine that you have your laboratory, and next door your biggest competitor also has a laboratory, and there's a lot of animosity, and unbeknownst to you, there's another input here on this operation. Sorry, you don't know about it, but they know about it, and so you run your experiment, you get some result, and then you run it again, and the next time they send in a system, some different system, and you'll get a different probability the second time you run the experiment, and so it looks like you can't reproduce your results. So what this assumption is doing is telling you that you've fully characterized all your pieces of apparatus so that your antagonistic colleague next door cannot mess with your results. Yeah, so that's kind of why you need it. Yeah.
So I guess if I understand well, it's indeed to account for the not perfect information setup that represents your circuit. It was a naive question in the sense of when I have a circuit, I have a circuit. Mm-hmm. What you're trying to say is that what if it's not the desired input and the desired output,
yeah,
right?
Yeah. What if you don't really have control over your apparatuses like you think you do? Yeah.
Thank you very much.
So this assumption is a way of saying, well, we're going to assume you do.
Okay.
But you mightn't. Yeah.
Thanks.
Yeah. It pays to be paranoid, I think, is the. Okay. So now what about equivalence? And I've just written this in words. You say that two operations are equivalent if you have the same probability when completed into a circuit for any such circuits completing it. So let me explain that using my hands. I should perhaps have drawn a picture. Imagine I have operation B or operation C. Well, I can put some circuit around operation B, and I'll get a probability. I could put the same circuit around operation C, okay, and maybe I'll get the same probability. If for operation B and operation C, I always get the same probability for any circuit I put around them, okay, then those two operations are behaving in the same way so far as probability is concerned, and so we say that they're equivalent, okay. So this is a very basic notion of equivalence. And we can go a bit further and extend this notion in a linear fashion by defining what I call the P function. So the P function is defined like this. You can apply the P function to a sum of circuits multiplied by real numbers. So alpha and beta, etc., are real numbers. So I multiply circuit 1 by a real number plus circuit 2 by a real number, and then that should be equal to, the way this function is defined, that should be a definition. Alpha times the probability for circuit 1 plus beta times the probability for circuit 2. So I'm just defining this function like this. I can certainly do that. And if you do that, and I won't go into all the details, then you can make statements like this. You can say, well, alpha times some operation plus beta times some operation is equivalent to gamma times some operation plus delta times some operation. You can use, so what you just do there is you just complete, you complete these operations into a circuit, and then this has this, for this equivalence to be true, you have to get this for any such completion, and you're using this P function. So this is very useful because you started off by describing stuff in a laboratory, and now you've managed to put some linear structure on that. Okay. And this is a very general sort of thing you can do. This is not restricted to quantum theory. You know, really, if you have any sort of probabilistic theory, you can do that. And it doesn't even have to be probabilities. Maybe you're interested in a different quantity, in which case you would define, you know, rather than probability in a P function, you define some quantity for that thing instead. Okay. So, so now let's define what I mean by time symmetry. What I mean is that for every operation here, B, there is a mapping to a time reverse operation. And really these mappings just have to be between equivalence classes. Okay, so you can see that this one is turned, rotated it through 180 degrees. So this one is upside down, so to speak. It's the time reverse of that one. So there's a mapping like this, and it has to be the case that under that mapping, for every circuit, if we time reverse it, we get the time reverse like that. Okay. Is that clear? So that's what I mean by time symmetry in operational theory. And what that means is that for any process that you have, there is a process that looks like that, but described in the reverse direction. Okay. It's not the only definition of time symmetry you could think of, but it's a good one, I think. Okay. Okay. Now, physicality. So physicality is, in some sense, the idea that sort of breathes physics into this framework. This is what makes it about physics. Physicality consists of, well, you need three things to be true. First of all, you want that your probabilities that you get for your circuits are between 0 and 1. So there's the positivity and the subunity properties. And then you also want certain causality conditions to be satisfied. And I'll come to the causality conditions. They're interesting, I think, in the time-symmetric setting. Now, it turns out that causality implies subunity. This is something I haven't fully understood yet. I think there's something interesting there, that this basic property subunity is implied by the notions of causality that are used. It may not be true for any notion of causality, but for the notions of causality that I'm going to use, they do imply subunity. And now one thing that's important is it's possible to impose a positivity and causality conditions on the individual operations, and that guarantees that any circuit satisfies these physicality conditions. It needn't be like that, and perhaps there are theories where it isn't like that. It might be that in some theories, it might be that you cannot achieve physicality by imposing conditions separately on the operations. But in the kind of theories I'm interested in, you can do that, and quantum theory is like that. Okay. Okay. Well, positivity is really just the same concept you have in the standard time forward picture. You just want to be sure that every time you put your operation inside a circuit, you get a probability that is greater than or equal to 0. Okay, and in the quantum, in the standard quantum literature, that's called complete positivity. Okay. What's more interesting is causality, so let's look at that. Okay. Well, okay, so it turns out in the time-symmetric approach, we need a forward causality and a backward causality condition. Forward causality, sorry, yeah, let me define this, the basic forward causality principle. Well, let's try this. We cannot signal from the future to the past, okay? So if I make some choice in the future, that shouldn't influence probabilities in the past. That seems like a good principle. But we're in the time-symmetric setting, so that means we also need the basic backward causality principle. We cannot signal from the past to the future. I'll take a sip of water and pause at that point. I should maybe be drinking something harder than water. Well, that's not very good, because if we can't signal from the past to the future, then what is going on? So let's modify that second one just a little bit, unless we condition on incomes in the past. Okay. So if I condition on some stuff in the past, then I can signal to the future, and that's kind of the experience we have. We have more special information about the past, and conditioned on that, it's possible to send information into the future. Well, the thing is, we need to be time symmetric, so that means we also need that. We cannot signal from the future to the past unless we condition on outcomes in the future. Okay. So those are our basic causality principles, and then we can turn those into conditions that apply to operations. And I'm not going to go through all the steps as to how you get here, but the basic idea is that if you place these boxes on the, so the first condition, this one here, is the forward causality condition, follows from the basic forward causality principle. If you place these boxes on the outcome and output of your operation, so you're basically ignoring that rather than conditioning. This is the opposite of conditioning. This is ignoring the future. Then that's equivalent to having these boxes on the income and the input here. Okay. So that's the notion of forward causality. And this, in the standard quantum picture, is the same thing as saying that that maps should be trace preserving. So for those of you familiar with that. Okay. But then we also need the backward one as well, which is like this. Okay, here. And yeah, so it's just the same thing, but the time reverse. Okay. So these conditions are sort of basic to the whole framework. And I've given you the conditions in the case where these are deterministic operations. If they are indeterministic, you have to put a less than or equivalent symbol instead of the equivalent symbol. Okay. Okay, so now let's, sorry, I didn't notice when I started. How am I doing for time? What's the sort of? Okay. Okay, so speaking very quickly, we'll now talk about the operator tensor framework. So, so we have, I mentioned this on the first slide, we have a correspondence from these things which are in the laboratory to these things which appear in your notepad. These are mathematical objects. We want this correspondence to be such that, and I'm going to show you on the next slide. I'll finish that sentence on the next slide. Before I do, let me mention what these objects are. So these mathematical objects are things that live in a certain space. So associated with each pointer, we have a vector space, And then associated with each of the systems, we have a space of emission operators. Okay, so the details are not very important. These objects are mathematical objects. They live in a certain space. Remember, I said I was going to finish the sentence. So this correspondence is such that this is true. So the probability of any circuit is equal to the same circuit, but where now you replace each operation by the corresponding operator. Okay, and you do that throughout. And this works for all circuits. Now, it's possible to set up that correspondence in a very natural way. I don't have time to go into the mathematical machinery as to how that works. But it needs certain assumptions, which I won't go into. But I think it's very nice because what you have is that the calculation for something in the laboratory is given by a calculation. This thing here is a calculation that looks the same. Okay. So I think all physics should be like that. Every time you do a calculation, you should just turn a picture of the thing into a picture, which is the calculation, and then it gives you the answer. Okay. And one of the things about this correspondence principle is that any sort of relationships we have between operations, like equivalence relations, they go over to relationships between operators. Okay, so we had these double causality relationships, for example. We get the same relationships for operators. The one difference is that here we have equality rather than equivalence. That's a detail. Okay. Okay, and then in this framework, you can write down axioms for operational quantum theory. So here, some axioms. Basically, the axioms say that the operators should be physical. That's basically the idea. Okay, and finally, the Hilbert objects. Well, I don't really have time to talk about that. This is adding some extra mathematical machinery that you can use to prove all sorts of theorems and do calculators. It's essentially the doubling up, for those of you familiar with that. I'm pleased with this notation I have because now it looks, this operator here, it looks like you just split it in half and then you draw a wire between the two halves, which represents summing over a certain label K. Okay, so this is the sort of overview of the framework. We go into the laboratory, we draw pictures of stuff in the laboratory. We use this P function to set up operational equivalence. It allows us to have some notion of linearity, which is very important. Then we set up correspondence, and there's a lot of mathematical machinery that goes into that, which is in the book. These Hilbert objects are very useful because they allow us to prove theorems over here. And so now I've sort of shown you that kind of picture. There's a, well, maybe because Gilles is in the audience, I should mention teleportation. So one thing you can do in this framework is you can take your favorite quantum experiment and turn it upside down, take the time reverse, and see what it looks like. And you know, if you take a painting and you turn it upside down, you kind of, you get a different view on that painting. You know, apparently if it's not a very good painting, you can see the errors. There's that famous picture that you've probably seen where you have a face and it looks like a normal face, but when you turn it upside down, it's hideous because they've rotated, in the original picture, they rotated the eyes and the mouth in a funny way that you don't notice when you look at it the right way up. When you turn it upside down, you can see that. So teleportation passes the test, of course. I wouldn't say otherwise because Gilles is here. There. So this is standard teleportation, but it's described in this framework. So what you do is you have noise comes in, R just represents classical noise, and then you get a subvalue of X, okay, the readout. And we're going to just consider the case where x equals 1. So that will happen probabilistically. And that will prepare a certain Bell state. Okay. And then we send these entangled photons, let's say, or particles. And then over here, we do a Bell measurement. Okay. The Bell measurement will have an outcome, which is represented by 2 classical bits here. And then we use those 2 classical bits to choose a unitary operation. And then this system that comes out is in the same state as the system that went in. That's teleportation. The way I've drawn it here, it only works when you get the right value of x. But you could condition on that. Well, the time reverse is just given by rotating that picture upside down and putting tildes on to indicate that you've done that. So let's see what happens now. What happens now is you send a system in. This C is the time reverse of this. So now you get 2 classical bits of information out, and your system carries on. And then you use these 2 classical bits of information to choose a Bell state. Okay. And then one half of that Bell state goes up here, where you make a Bell measurement. Now, if you get the right value of x, your teleportation works, and the thing that comes out here is the same as the thing that went in. So it's teleportation, but upside down. It only works when you get the right outcome of x here. Now, in the forward time direction, normally we imagine we can pre-select on a certain value of x. In the backward time direction, you just have to hope you get the right one. You can model these C gates like so. I'll skip past that. Okay, well, the complex case, I won't talk about this in any detail. The main thing is that associated with every operation now, you have a causal diagram because it's causally complicated. And then you have double causality conditions, which are more interesting, much more interesting, I think, in the complex case. And then you have the same story as before. And you can also have axioms in the complex case as well. Okay. So the conclusions. We have this time-symmetric formulation of quantum theory, which is, in the simple case, equivalent to the standard time-forward framework. I haven't actually proved that it's equivalent in the complex case, and there's something very interesting there, maybe. I think this formulation is more fundamental because it's linear. So this might make it suitable as a launching pad for quantum gravity. In the book, there's a lot of developments that you're welcome to go look at. So lots of discussion about causal dilations. I prove various composition theorems. If you put together 2 operations that are both physical, you want it to be that the combined operation is also physical. So that sort of thing is proven in the book. And then there's another interesting thing. I don't have time to talk about it, but I think it's interesting, so I want to just point to it, is Raphael Sorkin had this thing called impossible measurements. These are measurements that sort of need to be ruled out, but it's not clear how to do it in quantum field theory. There's been a lot of work on that recently, and in this book, I show how to rule them out using these physicality conditions. And that's it. Thank you.
Thanks a lot, Lucien, for a really interesting talk on a very nice subject. Do we have any questions from the audience?
Thank you. I was wondering if this approach brings some light to the measurement problem.
Right. No. Well, let's see. This is sort of an indirect way of answering your question, but there's the Stein spring dilation you may be familiar with. So this is where you say that any measurement can be represented in the form. Any measurement, it might be a measurement that takes, or any general evolution. It might be one that takes pure states to mixed states. It can be represented in a form where you introduce another system, an ancilla, and then you perform a unitary evolution on that bigger system, and then you trace out the ancilla. Okay, so this is called the Stein-Spring dilation, and it relates to something that John Smolin called the Church of the Larger Hilbert Space. Okay, so in the Church of the Larger Hilbert Space, you always want to find a bigger system so that your evolution is just standard unitary evolution in quantum theory. And then because you believe, perhaps for religious reasons, that this should be the case. Okay. And so the Stein-Spring dilation theorem is important because of its religious significance, and it kind of relates to the measurement problem because you can always do this. And it's also important because it provides a mathematical representation of general operations. Now, it turns out that in the time, and the other thing it does is it provides for what I call a peaceful coexistence between the Church of the Larger Hilbert Space and the Church of the Smaller Hilbert Space. The Church of the Smaller Hilbert Space, that was a term coined by Matt Leifer. He has a blog post and also a Facebook group you can join. So those are people who don't believe that you should always make a bigger Hilbert space. You should just stick with what you've got. There's no religious reason to enlarge your Hilbert space. Anyway, the Stein-Spring dilation allows peaceful coexistence between these two different churches. There's no need for religious war. However, in the time-symmetric approach, that peaceful coexistence is broken. And I'm not sure word has gotten out yet, but this means that you can't think in this time-symmetric approach that you can always enlarge your Hilbert space and then find a unitary evolution. Well, I should say it looks like that's the case. There is some conjecture in the book you can read, but the evidence is piling up in favor of that breakdown of peaceful coexistence. So that makes the measurement problem worse, not better, I would say. Yeah, but that's good.
Okay, thanks.
All right, we have time for one very short question, if anybody has a very short question. No very short questions? Okay, then let's thank Lucien again for the great talk.